mathematical modeling, setting up a differential equation. So in this course so far, we've looked at lots of different relationships of functions. And in the functions we've looked at, we've been describing a relationship between one dependent variable and either one or multiple independent variables. And we studied the behavior of what happens as we change and vary those independent variables, what happens to the dependent variable. So this all relies on the relationship between these types of things. In setting up a differential equation, we're going to be defining a new type of relationship that we haven't looked at before. However, we have looked at pieces of this in small ways, and now we're going to put it all together. More on that in a minute. One algebraic property that we're going to need to remember that comes up a lot when talking about differential equations is the idea of proportionality. So again, this comes from algebra, so it may have been a while since you've seen it. When we talk about the relationship between two variables, we say y is proportional to x if there's a non-zero k such that y equals kx. So what that means is that the relationship between the independent and dependent variable here are related by this factor of k, which is a constant and it's not zero. An example of this is your pay. So let's say you get paid $20 an hour. So if y is your total pay and k is $20, then x would represent the hours worked. Now as x increases, y increases because k is a positive constant in this scenario. And if x decreases, then y decreases. So they do the same thing. We also have what's called inverse proportionality. So we say y is inversely proportional to x if there's a non-zero k such that y equals k times 1 over x. So again, the idea is that x and y are related, only now if they're inversely proportional, that means as x goes up, y goes down. So for example, let's say that y represents the total amount of time it takes you to drive from your house to an amusement park. And x is your speed that you are going or driving in your car. As your speed increases, the total time it takes you to drive is going to decrease. These are inversely proportional because as one goes up, the other goes down. So these words proportional and inversely proportional imply that we have this constant k, and again, that we are multiplying this k towards the thing we're describing when talking about this relationship. So, what is a differential equation? So a differential equation, instead of relating two variables, is going to relate a function with its derivative. Now, we have studied derivatives of functions using things like area under the curve or other types of analysis on graphs and tables. So this isn't entirely new, but either we've been just looking at the derivative or just looking at the function up until this point. So now we want to take these two things and use them simultaneously. In a lot of scientific fields, what's going to happen when we study differential equations is we're going to represent some sort of physical quantity with our function. And then the derivative is going to talk about how that thing is changing over time. And the differential equation is going to be what defines the relationship between the two. So we're going to look at a lot of examples of these. But in this particular section, what we're working on is just understanding how to take the words describing a situation and to set up a differential equation that represents what we are trying to look at. So we are just setting up these differential equations. We will look at how to solve and work with these equations in other sections. But for this section, we just want to set them up appropriately. Now, sometimes that means we have to choose variables. Sometimes the variables are given to us. So we'll look at a host of scenarios to see how this works. Example 1. A population of insects in a region will grow at a rate that is proportional to their current population. On any given day, 16 insects are eaten by the local bird population and 7 die of natural causes. Set up a differential equation to model the rate at which this population is changing over time. So since we're looking for a differential equation, we are trying to relate the rate at which this population is changing, or the derivative, to the actual population itself. So here we see that the rate is proportional to the current population. In this particular example, we are not given any variables. So the two things we're talking about here is the insect population and time. So we need to come up with variables that represent these two things. So I'm going to use P for population, and I'm going to use T for time. Now, if you're asked to set up a differential equation with no variables given, you can use whatever you want, but I strongly suggest that you use things that help you understand what they represent or help the reader understand. So again, we are trying to relate the derivative to the original function. So the original function here is going to be population, because population is the dependent variable between the population variable and the time variable. Time is what's varying, and so therefore it's independent. So when we talk about the derivative of population with respect to time, there's two different ways we can write this. We can write it as dp dt or p prime. The top notation is called Leibniz notation, and the bottom notation is called Newtonian notation. They both represent the derivative of the population with respect to time. So that is how quickly the population is changing over time. That's what the derivative represents, the change in population. So how do we set up this differential equation? How do we talk about this change? So we're told that it's growing at a rate proportional to the current population. So that means that the change is going to be K times P, right? So K is just a constant. I don't know what the number is. It's what we typically use, either C or K. Sometimes some books use A, but it's just a constant here. So the rate of change is going to be K times P. So some percentage of the population is how much we're changing by, right? So if K was 1, that would mean 100% of the population is what we're gaining with each change. If K was 0.5, that means we have 50% of the population is growing, right? So if K is positive, our population is growing. If K is negative, our population would be decaying. So here we have it's growing, right? We were told it's growing. So that tells me that my K here has to be greater than 0. So that K times P represents this first part of my example, right? So the insects are growing at a rate proportional to their current population. So K times P. So if the population was 100 insects and K was representing a growth of 20%, then K would be 0.2, P would be 100, and then 20% of 100 is 20. So the rate of change is 20 insects over time. Now, we also have this part where some of these insects are dying, right? So we have 16 insects that are being eaten and 7 that die of natural causes. So even though we have this growth, K times P, we also have a loss. Now the loss is a strict number, right? It's not related to anything else. It's just the number that we lose every single day. So here we're losing 16 plus 7 every single day. So 16 plus 7 is 23. And because we're talking now about how many we lose per day, that means that we have made the decision at some point in this model that time is going to be in days. Okay, so on any given day, the rate at which the population is changing, either dp dt or p prime, is going to be k times p, so the size of the population times k, minus 23. So these are the two different ways that we can write our differential equation. Now, in a later section, we will learn how to solve these for p and talk about what that means. But for now, we're trying to really understand how to set up this relationship. Let's look at another. Example 2. Let y of t represent the size of a population at time t. The population changes through births and mortality. Suppose that b, which is going to be positive, is the per capita average birth rate. So how many new babies are we getting every single day? And m, which is greater than 0, will be the per capita average mortality rate. So how many people are dying every single day? We want to set up a differential equation to model the rate at which this population is changing. So here, we don't get to pick our variables because we have this y of t. So y of t tells me that y is my dependent variable that's going to represent the population. And t is going to be time. Now, it doesn't explicitly say that time is per day. So here we're talking about the average per capita birth and death rates. Those are usually reported per day, but they don't have to be. You can report birth rates and death rates per year, per month. So we don't know for sure. So it's probably per day, but we don't know. So we won't put an exact unit on it. So again, we're setting up a differential equation. So what we want to talk about is the rate at which the population is changing. So dy dt is the change in population with respect to time. We could also simultaneously write this as y prime. Those are going to mean the same thing. So we're talking about the change. So there's two different things happening. There are people being born and there are people who are dying. So we need a way to write each of these. So let's start with the birth rate. So the per capita birth rate, B, is much like our constant K. That is going to multiply the size of the population. It's related to how many people there are. That's the per capita piece. That's related to the size of the population. Per capita is per household. So we know that since it's growing and B is greater than 0, that we should have a positive B times Y to represent the growth. Now, simultaneously, we have people dying at this rate of M per capita. So again, that is also related to how many households there are or the size of the population. And since we're talking about the rate of change, we're going to subtract off the people who are dying, right? So the BY represents the growth of the population, and the MY is the decline of the population. Now we could factor the Y out. So on the bottom version of this, I will, just so you can see the different ways that this could be written. But here, if B is bigger than M, then our population is growing overall because more people are being born than are dying. But if M is bigger than B, then we'll have a population decline because that means we are losing people on average. So this is a way to relate the change in population, right, with the current size of the population, and therefore we get a differential equation. And again, you can write this either way depending on your preferences, what the problem is asking for, or the textbook you're using. And again, they represent the same thing. So again, we're relating the derivative of the population, so how much it's changing over time, with the actual variable for population. Let's look at another example. Example 3. Suppose that, left alone, the deer population in a particular state increases at a continuous rate of 30% per year. Suppose that deer are also hunted at a constant rate of 6,000 deer per year. We want to set up a differential equation to model this. And by this, I mean the deer population. So again, since we're talking about a differential equation, we're asking how does the deer population change over time? So again, back in this scenario, we don't have any variables assigned, so we want to use variables that make sense. I'm going to use P for population. You might have chosen D for deer population. That would be fine. And T is time. And time here is defined, okay? So time is going to be per year, so time is in years. Another thing that we know here is our K. So K is 30% per year, which means that we can let K be 0.30 because we know exactly how much it's changing. So when I set up my differential equation, I'm going to again start with my derivative. So dp dt, or P prime, whichever you prefer. So the rate at which the deer population is changing is going to be 30%, so 0.30, times whatever the population is. Now, I don't know how much the population is, but if we had, say, 100,000 deer and we were growing at 30% per year, then we would do 30% of 100,000, which would give us 30,000. So that would be the derivative, right? So we're talking about the growth, right? The derivative is the rate of change. It would be 30,000 per year in growth. However, we also have that they're being hunted at a constant rate of 6,000 deer per year. Now, that 6,000 does not depend on the size of the population. There might only be 6,000 deer, or there might be 6 million deer. We don't know. But they're being hunted at a constant rate that's not related to the size of the population. So we're going to do minus 6,000. Because no matter what, the growth that happens in any given year is 30% of the population is how much it grows, minus the 6,000 that were hunted, and that tells you the change in population for that year. So what's important here again is that we are setting up our differential equations, and again, you can write it either way, but also the information we have about the variables. The time is in years, that our rate here is 30%, so that we can talk about and describe what is happening mathematically. So that's how we set up that differential equation. Let's look at another one. Example 4. After a bicycle accident, a person takes Advil at a rate of 100 milligrams per hour. The rate at which the drug is exerted from the body is proportional to the quantity present, with proportionality constant 0.2 if time is in hours. Set up a differential equation to model the quantity Q of the drug in the body over T hours. So we're given our variables here. We're told to use Q for our quantity and T for our time. Q is going to be our dependent variable because the quantity depends on how much time it's been. So our independent variable is time in hours. And our proportionality constant K here is 0.2. So when we set up our differential equation, we are interested in how the quantity changes over time. So either dq dt or q prime. The things we need to incorporate is the amount of the drug going in, which is 100 milligrams per hour, and the amount of drug that's being let out. So the exerted part of 0.02 with our constant of the quantity. So the 100 milligrams per hour does not depend on the quantity Q, right? It's just a number. Every hour you're getting a new 100 milligrams. It's not related to how much is already in there. So the 100 stands alone. And it's positive because it's going to increase the quantity of the drug in the body at any given time. Now, the rate at which the drug is leaving the body is proportional to the quantity present. So it's related to this Q. So that means we have this 0.2 Q as the amount that's leaving the body. Since it's leaving the body, that means we need to subtract it off. So our differential equations look like this. If we are trying to determine if our quantity of drug in the body is increasing or decreasing, it depends on the value of Q, how much quantity of this drug is currently in the body. So for example, if Q equals 10, right, then if there's currently 10 milligrams of this drug in the body, then when we multiply that, we get that dQ dt would be 98, because it would be 100 minus 2. Now 98 means that we are increasing the milligrams of drug in the body by 98 milligrams every hour when Q equals 10. So that's increasing because it's a positive number. Similarly, if Q is currently 600 milligrams, then our rate, we would do 100 minus 0.2 times 600. 0.2 times 600 is 120. So 100 minus 120 is negative 20. So if there were 600 milligrams of the drug in the body, and we were only taking 100 milligrams per hour, then at that particular time, we would be losing 20 milligrams per hour. So our function would be decreasing. So whether or not our differential equation, our derivative, our function is increasing or decreasing depends on the current value of the dependent variable, right? So when we talk about whether or not our function, when we're talking about Q, whether or not it's increasing or decreasing, we can look at the sign of the derivative. And if the derivative is positive, then Q is increasing. If the derivative is negative, then Q is decreasing. And those are things we had talked about back in Calculus 1 that still work here. But again, it depends on the current level of Q, or the current level of the dependent variable. Let's do another. A person deposits money into an account at a continuous rate of $6,000 a year, and the account earns interest at a continuous rate of 7% per year. Write a differential equation for the balance in the account B in dollars as a function of years T. So again, we are given our variables here. We are told that the dependent variable is B, the balance. Our independent variable here is time. So when we talk about setting up a differential equation, we're looking at how the balance changes over time. So dB dt, or B prime. So we have money coming in, but we also have money that is interest being earned. So there's two different positive money streams that are happening here. We're not losing any money from the account, but we have to take a way to write in both money streams that are impacting the balance. So the first one is $6,000 a year. So that is not at all connected to whatever the current balance is. It doesn't matter if we have $10,000 now or $100,000 now. We're just putting in $6,000 per year. So since that's a constant, we just write in 6,000. That's not at all related to the balance. It's just how much you put in. Now, we're earning interest at a continuous rate of 7% per year. When you earn interest on money, the amount of interest is based on the amount of money you have. So this 7% is directly related to the balance. It's going to be 7% of the balance you currently have. So we're going to put 0.07 to represent 7% times B. 7% of the balance is telling us how much our balance is going to change. Remember, we're modeling how much our function changes, not how much is in the account, but how much did it change from year to year, right? The derivative. Now, since this is also positive and we're gaining money, this is going to be a plus situation. We have two streams of income, but they're both making your balance grow. So it'll be 6,000 plus 0.07 times B. So again, if we wanted to get the actual rate of change, we would need to know the balance B. And we could figure out how much the balance was changing at that time, but we would need to have a value of B to plug in. But this is how we set up our differential equations for this type of problem. Finally, we're going to talk about the differential equation that models logistic growth. Logistic growth is a really important concept in biology that we can start to look at through the lens of a differential equation. Logistic growth is also studied in Calculus 1 by looking at rates of change and inflection points. However, there's no discussion on where that function comes from. So by starting to set up the differential equation for the factors that model it, we can start to understand how we get the logistic growth equation from the differential equations that we set up. So remember, a logistic growth model talks about how a population grows over time. It has a carrying capacity, which is the largest that the population can grow to attain. And that's based on a whole lot of things like resources, the size of the land, predators, all those sorts of things. So the carrying capacity we call L. So a population in a confined space, right? So maybe on an island, it might be the entire United States, but all space is confined in some way, is going to grow proportionally to the product of the current population and the difference between the carrying capacity and the current population. So remember, carrying capacity is the maximum population that can be sustained. So we want to set up a differential equation for the population P. So population here is our dependent variable, and time t is our independent variable because we're looking at how it's changing over time. So when we set up our differential equation here, we're going to have dp dt. And what this says is that it's proportional. So remember that we're proportional. So we're going to have a k to the product. So that means we're going to be multiplying two things, right? Product means multiplication of the current population P and the difference between the carrying capacity and the current population. So we have K times P times L minus P. And we're told here that this is growth, right? It's logistic growth. So that implies that K is going to be positive here. This is called the logistic differential equation. This is a really important equation in biology to help us get to the logistic growth model. But this is how we set it up. So when we look at what's happening in this differential equation, I want you to notice that when P is small, the derivative is also going to be small. And that means that the population is growing slowly. So if P is small, that means we're multiplying a small number times K, which is going to be smaller, times L minus P. So that's going to be sort of keeping things small. Now, as P gets bigger, right, so if we increase P, then our derivative is also going to get bigger. Because remember that P is never going to be bigger than L, because L is the maximum it can be. So that term is always going to be positive. We know that K is positive and the population is positive. So as P increases, then our derivative also increases. It grows more rapidly. However, as the P gets closer to L in this second term, that second term is going to get smaller and smaller, which means we're going to slow down the growth, and our derivative will get smaller as P gets closer to L. So when P is small, we start near the beginning of time, and our derivative is small, so it's growing slowly. Then near the middle, we're going to grow pretty rapidly, right? When P is not too close to L, but not tiny. And then near the end of our growth, right, then our derivative is going to be small again or slowing down. So this relates directly to the picture that we used in Calculus 1 to talk about logistic growth models. So when P is small, we're growing slowly. So notice that the derivative here is small. If you were to draw on some tangent lines, they'd be pretty close to horizontal. And then in the middle is when we have rapid growth because P is increasing. So our derivative is going up. It's growing at a rapid rate. But then when we get closer and closer to L, we start slowing back down because our term L minus P is starting to decrease and therefore making our derivative small again. So our picture that we've used before, now we can reason through it by talking about the differential equation that models logistic growth. So again, this is a really important differential equation that has a lot of implications in the life sciences. So we'll be looking at this in a few different contexts now that we know how to set it up.